Hello everyone, very good morning and welcome back to chapter 3. Another exciting video in this DSA JavaScript series. But in today's video, we will not use any specific language as this series belongs to JavaScript, but we will not use either JavaScript or Java or C++, anything. We will simply try to understand what is big O notation and why it is required. And as usual, we will use some real world examples to understand those things. Okay, without further delay, let's get started. This chapter introduces big O notation. The name sounds complicated, right? And everyone get afraid of it. How to calculate big O notation, how to calculate time complexity, how to calculate space complexity. But it's the language we use to describe how the runtime and space requirement of an algorithm grow as the size of input increases. Mastering Big O is not just about passing technical interviews. Keep it in mind. It's about writing efficient, scalable, and professional code. So, what is Big O notation? Big O notation is a mathematical notation that classifies algorithms according to their time complexity, how the execution time grows, and space complexity, how the memory uses grows. It describes the worst case scenario performance, giving a reliable upper bound on an algorithm's growth rate. Okay, don't worry if it sounds complicated to you because, as I said, we are going to use real world examples, no technical things for now, okay, to understand what big O notation actually is and how we will calculate time complexity. Okay, why do we need big O? A very important question. Is it only to pass technical interviews? No, it is to calculate the time complexity, means how much time our program will take, right? But is it the actual time that we are going to calculate? No. Why? Because if we calculate the actual runtime, then it may vary from computer to computer based on your hardware. If you are using a legacy system, an old system, okay, and your processor is not that much fast, then it may take more time. But if you are using a faster processor, then you may do it quickly. So are we calculating that one? No, we are not calculating that one. Then what we are calculating? When it comes to time complexity, when we are saying that we are calculating the running time, then what actually we measuring? Now, to understand this, we have to understand dominant term. This is a important thing to understand while calculating all those things. Now, in the context of big O notation, the dominant term is the part of an algorithm's complexity formula that grows the fastest as the input size gets very large. It is the only term we ultimately care about when determining an algorithm's big O complexity. Okay, think it is think it in this way. The dominant term dictates the shape and steepness of the performance curve when n is big. Now, let's take this example. If you are a student or if you are a working professional, whoever you may be, but definitely you are going from home to somewhere. Okay, Think of this scenario. Suppose you are going from your home to somewhere else through metro. Then what you have to do? You have to walk from your home to the metro station. Then from metro station, you will go to that point through train. Right? Now, the walking distance from your home to metro station is always fixed. It may take 5 minutes, 10 minutes. Okay. In our example, let us say it's taking 5 minutes. Now, you are going to different places by metro. So suppose your distance is 1 kilometer and it takes 10 minutes. Train time minutes for 10 miles. Okay. In this example, we have taken that in 1 minute it covers 10 miles. Okay. Today you are going to a distance of 20 miles through train. Then how much time it will consume? Your walking distance is same 5 minutes, right? It is not going to be increased. But by train, you are covering 20 miles. So it will take 2 minutes. So total commute time is 5 minutes plus 2 minutes. 7 minutes. Okay. Now, next day, you are about to go 100 miles. So if you are going 100 miles, then will your walking distance from home to metro change? No, it does not change. It always remains constant. It remains same. But the time that changes is the metro time. Okay. As you are covering 100 miles, so it will take 10 minutes. Now the total commute time is 15 minutes. Okay. Similarly, suppose your train time is 1 hour, then total commute time is 1 hour 5 minutes. So gradually, as your train time increases, your total commute time increased. Okay, so which is the dominant term? The dominant term is the train time. The train time means the distance that you are covering by train. That is your dominant term. Okay, so while calculating time complexity, you have to analyze which is your dominant term, and you have to focus on that, how you can optimize that term. Okay, now how you can optimize? Can you optimize metro train time? No. But what we are trying to say here, the train time that you are covering, if you are covering that by bus, okay, suppose two persons, you and your friend Ramesh, both started from house, your houses are nearby, okay, so you started from your house and you went to metro station, he went to bus stand because bus stand was nearer, okay, so he reached bus stand within 1 minute, you reached metro in 5 minutes. Got it? Till this point, your friend Ramesh is faster. But after that, both are going to cover 100 miles. You covered it by metro, and your friend Ramesh covered it by bus. So definitely covering 100 miles by bus will take much more time as compared to covering it by metro train. Right? So you optimized the time required for that specific operation by covering the dominant term, the actual distance covered through metro. But another person covered that time through bus. Okay. So both bus and metro by both the medium, you can reach the destination. That is correct. Okay, but you will reach early as compared to your friend Ramesh. So you optimized your operation. Okay, you did it in less time. That's the point. Got it? So if we are not looking that in a broader picture, okay, let us say that we are covering only 1 mile of distance. So in that case, your friend Ramesh may reach early because the walking distance that he covers from home to bus stop is very less as compared to your time. Okay? You took 5 minutes to reach metro station, then 1 minute to reach your destination. So total commute time is 6 minutes. Your friend started from home to bus stop with only 1 minute time, and then in another 1 minute he reached the destination. So your friend reached the destination in 2 to 3 minutes, and you reached in 6 minutes. So when the total commute, the total distance that we are going to cover is only 1 mile, your friend may reach early. But when the total distance is 100 miles or 1000 miles, you will reach early. Okay. So writing a program is easy. Anyone can write a program. And if you are calculating the time when the program is not that much scaled, means you have not considered all the things. As we discussed here, the commute time is suppose 1 kilometer. Okay. And you are not seeing any difference. You say, yeah, it will also work fine. Okay, there is no issue. But have you verified when your distance increases, will it perform efficiently? Okay, in real world examples, you created any e-commerce app. Okay, but as you created locally, you have not deployed anywhere, and even if you deploy, there may not be users. Okay, only you and your 3, 4, or 5 friends are using that. Then, if we deploy the same thing for a large e-commerce store, maybe Amazon, Flipkart, or anything, will it perform in the same way? Okay, if clicking on go to cart in your application takes 2 seconds, will it take same 2 seconds when the user base, the recurring users, mean at a time, suppose more than 1 million users are using that application, will it take the same 2 seconds? Okay, those type of calculations are important. That's why we are learning Bigo. Okay, so now you understood the dominant term. You have to understand which term dominates your complete calculation or your complete performance. So here you can read this example completely. I have explained with proper table and calculations, everything. Okay. So when the total distance is 10 miles, walking time is 5 minutes and train time is 1 minute. So total commute time is 6 minutes. But when it increases to 10,000 miles, the walking time remains same 5 minutes, but the train time, it increases to 1000 minutes. The total commute time is 1005. So here we observe that this train time increases as our distance increases. So we have to optimize this one. Okay. In the brute force approach, means when you start your program, at the time, if you have not thought of train, then that's fine. You can take bus. But once you completed the program, then you have to think how I can optimize this and how I can achieve this in efficient time. Okay, now let's continue to our chapter again. So time complexity, it measures the number of elementary operations like comparison, assignment, arithmetic. We will discuss everything again when we will actually discuss the concepts like array, linked list, stack, queue. Okay, at that time we will discuss these things again. Don't worry for that. In this chapter, we are just trying to understand why we need all those things and how it is calculated. So you will not get confused at that time, and that will be a revision for you. Okay? Then space complexity, it measures the amount of auxiliary memory, excluding the input itself. Whatever input you gave, you need memory for that. That's fine. But the auxiliary memory, the extra memory that we need while performing those things, okay, that we will calculate while calculating space complexity. Now, the most common big O complexities means the most common notations that we are using while explaining our complexity. The number of operations, big O of n means it can be done in a constant time. For example, assessing an array element. Let's look at this real world example. Library. This image is open here. Okay. Suppose your library has only 10 books and someone said, I need the book which is in third shelf. Okay, or I need the third book. So it took you suppose 5 minutes. And you have a library like this where thousands of books are there, and someone told you go to the third shelf or third rack and pick the fourth book. Okay, how much time will it take? Same 4 to 5 minutes, right? Now let us say the library has millions of books. So you may have to go 2 meters extra to go to the 10th rack or 20th rack. Not much more than that. So that's why we are saying here the time complexity is big O of 1. Means even if you are scaling your application from 10 books in the library, you went to 10 million books. But assessing a book will not take that much of time because we are maintaining the book number, the self number, the row number, etc. Okay. In array form, we are calling it the index of that specific element. So we know where it is. Okay. For a person, it took time to go to that specific self or to go to that specific rack number, but computer don't take time. Then you specify index number. Okay, even if you have millions of elements, it will reach at the same time. In that case, we say that our time complexity is constant time, big O of 1. Okay, it is very efficient time complexity because how much you scale that don't matter. The operation will be performed at the same interval of time. So this you have to explain to your interviewer that you are going to use this data structure. In this case, we are using array, right? In this library example. So you are going to use array data structure to solve this problem. So your time complexity will be big of 1. First, you have to explain this clearly to your interviewer. Then you will start writing code in the language which you know. That may be Java, JavaScript, C++, anything. Okay, does it make sense? Now, The next complexity is logarithmic time. Logarithmic time means the number of operations grows very slowly when the input size it increases. Okay. What does it mean? Let's take a real world example, because if I'm going to explain binary search now, that will be going to a little bit tough. So as I told you, we will not go to technicality now, we will just understand the concepts. Okay. Open image in a new tab. So let's take the phone book analogy. If we are trying to search a person's name in our phone book, okay, then what we are going to do? Let us say we have n names to search or n pages to search. Okay. So step one, we will open the phone book exactly at the middle and you look at the names. Then you decide, is the name that I am searching is before this hub or after this hub? If it's before, then we no need to search in the second hub because the name is not there. Okay. Why? Because everything is sorted in the phone book, right? From A to Z. Let's say I am trying to search my one of my friend whose name is Dibakar. So Dibakar starts with D, right? I opened from the middle of book and I saw the names starts from M. So if the names start from M, I know that D is between A to M. I no need to search for the second hub. What I will do, I will leave the second hub completely and search only in the first hub. Then I will again pick the middle portion and divide it into two. Now I saw that the middle letter is E now. The middle page which opened have only E letter names. So I know that it exists from A to E. Okay. So in this way, if the phone book has 1024 names, then we we would need only 10 steps to find the correct place. Okay. Here in this example, in this image as well, we have explained those things. Now, think in this way. Suppose I am searching for letter M, and as I told, the middle contains the letter M. So in the first iteration itself, I will directly go to the page where the M name exists. But if I go through the pages one by one, then it will take much more time. Okay. So this type of search we call binary search. Means we make it half whatever we are searching and then search only in that half where we think that it will exist. Okay, discard the other half. Then again we are making it half, okay, and look at for that specific half where it may exist. Okay, that's the way. Now let's go to our next one, linear time. Linear time means the number of operations grows proportionally to the input size. As we discussed in this dominant term, the train commute time, right? It is a linear time. So if 1 mile is covered in 1 minute, then 10 miles can be covered in 10 minutes. Okay, 20 miles can be covered in 20 minutes. You can calculate the time, the number of stops, the train stops, that will also take time, right? But our dominant term is the distance. Okay. here we have taken another example, that is shopping cart analogy, grocery cart analogy. A cashier is scanning the items at a grocery shop. So suppose it takes 2 seconds to scan one item, then it will take 20 seconds to scan 10 items. Right? Very simple. So many examples are there. You can find your personal example as well, and I would highly suggest all of you to think some real world examples on your own. Okay. Now the next one, long linear time. A combination of linear and logarithmic, n log n. Okay, linear time is big O of n, logarithmic time is big O of log n. Logarithmic time means binary search. We are searching it by making it half. Okay. Linear time means it will grow in a linear way. Okay, in multiples. Okay. Now log linear time is a combination of both. Now let's see an example of, okay, let's open a new tab. Okay, so playing cards. If you have ever played cards, then you may relate to it. But even if you have not played, you may have seen cards, right? So let us think that we are trying to sorting the deck of cards which is unsorted properly from 1 to 13. Okay, then how you will do? There are two different ways here. With this example, we will understand both quadratic time and log linear time, both. Okay. Now, first let's start with quadratic time, because it is the roast time complexity. We should not go for this, but it is the easier one to do. And most of the time, freshers go with quadratic time when solving these type of problems. Here I have mentioned everything step by step. So let's go through it. And it is a little bit tricky. I can say complex to understand. So please give attention to it. So what we will do, we have a deck of cards, right, which is unsorted. Let's say it is placed on the table or in our left hand, and sorted cards we will pick in right hand. So what we will do, we will pick one card and compare it with the cards which are sorted or which are in our right hand. Okay, so we picked one card. Now in our right hand, the number of cards is 0, or the sorted cards are 0. What we will do? We will pick one and put it in the sorted cards because it is the first card. No need to sort anything. That's fine. But for the next card, let us assume the first card is 4. We will go through this exact example. Then the second card is 1. So compare 1 against the card we already have. So we already have 4. Right? Now 1 is less than 4. So move 4 over and place 1 in front of that, because we want these two cards to be sorted. Okay. So now we have 1 and 4. Then I will pick another card. Let's say 5. And 5 is greater than 4. So what we will do? 1 and 4 are already there. Then we will put 5 next to that. Okay. Now say we picked another card which is 2. 2 should be in between 1 and 4. Okay. In this way, we will put all the cards. Now, if we calculate this thing, how much time it will take, then, okay, that calculation table I forgot to put here. Okay, not an issue. So generally, it will take the same number of times again. Suppose you have 52 cards, then you have to pick all the 52 cards, and in roast case scenario, the 52 number card, already 51 cards are sorted. So we have to verify it with all the 51 cards. Okay, that's why if we have 10 cards, then it may take 100 times in roast case scenario. If we have 5 cards, then it will take 25 number of times in roast case scenario. So it will take its square number of time that we call as quadratic time. Okay, if you have n cards, then it will take n square time. If you have 5 cards, then it will take 25 times. Okay? In roast case scenario. Now, how we can optimize this? That we can do through the logarithmic time, the fastest way. Divide and conquer. All the 52 cards we will divide into half. So 26, 26. Then again we will divide this 26 into half. 13, 13, and this into half. 13, 13. In this way, it, after some time we will get one card in each split. Right? And how many splits we have to do? For 52 cards, we need only 6 splits. So many examples I left here. Okay, but it is easy to understand, right? Okay, let's analyze it. So, yeah, it is here. Not this. Only merging I have explained here, but splitting not. Okay, so 52 cards. In the first iteration, we divided into 2, 26, 26. In second iteration, we divided into 13, 13, 13, 13. Right? In third iteration, again we divided into 2. So 6 and 7 cards, right? In each cutting. So in only in 4 iterations from 52, now each stack has 6 to 7 cards. Right? So after 6 iterations, there will be 52 stacks and each stack has only 1 card. Now, how we are going to merge it? So the total merging concept is little bit confusing. That's why I have mentioned all the 6 levels that we need, because we divided in 6 levels, right? So again we need 6 levels to merge it. So in level 1, what we will do? We will merge only 2 cards. There it is. Just a second. Yeah. So suppose we picked only 4. No, this is n square example. Okay, I will update these notes. Let me explain you manually. So now you sorted all the cards, right? Merge 1. Not okay. So we splitted all the cards, right? Now we pick the first 2 stacks. Okay, so there are only 2 cards, right? Let us say first card is 1, second card is 5. So we merged those 2, 1 and 5. The next 2 cards, let us say 7 and 2. So we will sort those 2. 7 and 2 means it will sorted as 2 and 7. right? Similarly, we will sort all those 52 cards into 26 piles now, right? Two cards are sorted. So now each pile has sorted cards. Okay, keep in mind. Then next time, okay, do you remember what we have earlier? Let's write it here. Let us say 1, 2, and sorry, 1, 5, and 7, 2. These are 4 cards. Okay. Similarly, we have 52 cards in 52 different stacks. Now, what we did, we collected 1 and 5 and merged them, but with sorting. So now we have 1 and 5 in first pile, and in second pile, we picked 7 and 2 and sorted them. So we have 2 and 7. Okay. So now instead of 4 different piles, we have now 2 piles, and each one has sorted. Right? Now, when we combine these two again, 1, okay, we took 1 from here. Now in this pile we have 5, and in this pile we have 2 and 7. So from this we will take 2. Now we have only 2 cards, 5 and 7. And we know that 5 is the next card and 7 is the next one. So only in 3 iterations we solved all these. Let's take some more cards. Let us say we have 2 more or 4 more cards here. Okay. So here 1, 2, 3, 4. 4 more cards, and in this level it will be 2 pile, and in this level we merged these two, and similarly these two will be merged into one more, and here there will be another step. Okay, so what happened, if we have 4 cards here, then we need only one extra step to add those things, right? Similarly, for 4 more cards we need one extra step. Okay, understood? So increasing only a step here, the number of okay, if we have only 2 cards, then we can cover it in only one step. If we have 4 cards, then we need 2 steps. Okay. If we have 8 cards, then we need 3 steps. And 16. Okay, let's do it from the top. That would be easier. We have 52 cards, right? Then we divide into 2, 26, then into 2, 13, then into 2, 6, then into 2, 3 cards, then into 2, 1. Okay, so it has only 6 steps where we covered 52 cards. If our card increases, let us say 104, then we have only 7 steps. Okay, and on these 7 steps again, if you look at here carefully, on each step, these are the number of steps. Okay, the total number of cards into, for each card we need a logarithmic time because we are bifurcating these things, right, from the middle. And when we bifurcate something from the middle and do the operation, that we know is the logarithmic time, right? So the total time consumed is the total number of cards multiplied by the logarithmic time, the total time complexity. So for 52 cards, 52 multiplied by the logarithmic time means 6. Okay. And if we have 104 number of cards, then the total time complexity is 104 times the logarithmic time means 7. Okay. If we have 208 number of cards, then the total time complexity is 208 times logarithmic time means 7. Okay. Now the next one, exponential time. So the number of operation doubles with every addition to the input size. Okay, it's become extremely slow when the size grows. Now let's open the link in a new tab, and here the example is the safe cracker analogy. Think of a safe when the image in a new tab. Okay, think of a safe. Suppose you forget the key combination of that safe and want to try every possible combination now. Okay. Now take an example. Suppose it has only one key. So means either you can switch it on or off. Only two combinations, right? 2 to the power 1. Now if you have two switches, then what would be the combination? Either both the switch will be on to open the locker, or one switch on, one switch off to open the locker, or one switch off, the other switch is on, or both are off. So there are four different combinations now. Okay. Similarly, if we have three switches, then we can have 8 different combinations. So in roast case scenario, it may take us 8 times to try the locker. Similarly, if you have 10 number of switches, then our key combination increases by 1024. Okay. So here you can see if you have only one key, okay, then we have only two combinations, on or off. That's fine. Sorry, if we have only one switch, then only on or off. If you have two switches, then we have four different combinations. But when the switch increases to 10, we have 1024,000 different combinations. So increasing only one switch increases our combination very rapidly. Means when we are going from 2 to 3, only one switch increased, but our number of combinations doubled. It increased from 4 to 8. Okay. Similarly, when we increase from 3 to 4, our combination increased from 8 to 16. So with an increase only one switch, it increased 8 times. Okay. That's the exponential time. The number of operations increase very fast as compared to the increase in the number of inputs. Okay. When number of inputs is 3, your output is 8. Okay, the number of key combinations, that is our output, right? That is 8. When it increased to 4, the number of key combinations now became 16. Okay, so with increase in one extra key, it increased 8 more combinations. Similarly, when we are going from 10 to 20, our number of switches increased by 10 only, but the total key combination increased in millions. Okay, so this is called exponential time in our time complexity. So from top to bottom, if you look at here, constant time is the most efficient time, but it is the most roast time that we are consuming. So if we can make it efficient, we can use better time, then we should, like as we saw in this example, that instead of quadratic time, we can use log linear time to sort the deck of cards. Okay. Now factorial time. The number of operations is proportional to the factorial of the input size. Now, let us see the example. The traveling salesperson problem. Think of a scenario where a salesperson has to travel different cities. From home, he is planning which city I should travel first, then which. So from which city should I go to which city so that I can cover all the places in less time and come home early. These type of calculations are covered through factorial time complexity. When you have only one city, you started from home, went to that city and came back. That's fine. But when you have two different cities, so you start from home, went to city 1, then to city 2, then came home. Or you start from home, went to city 2, then city 1, then came home. So you have now two different routes. Okay. And if you calculate factorial of 2, it is 2. Then when you have three cities, now you have 6 different routes. When you have 5 cities, you have 120 different routes. Okay. So this type of time complexity is called factorial time. So while calculating time complexity, you have to remember the dominant term as we discussed at the beginning. And bigger focuses on the growth rate. So constant factors are ignored. As in this case, this is the constant factor. Okay, always it will take 5 minutes from your home to metro. So no need to consider that. You consider only this while calculating time complexity. Okay. We only care about the term that grows faster as n gets very large. So that's it for now. You go through the notes, read everything what is written. You will get better idea. But whatever we covered in this session, overally, only this much is important, and this table, no need to buy at anything. Gradually, when we do more and more problems based on these things, you will be remember all those in your subconscious mind, and you will get acquainted with these type of things. What is constant time? What is logarithmic time? What is linear time? Okay. Thank you everyone for watching. We will meet again in chapter 4. Bye bye.